Okay, this is a Ph.D. defense for Luke Odell. Luke, most everybody knows him. He's been around here a little while. You've been here since 2013. He was here before that, in around 2010 or so, as a student who just took a class here in some of the classes, but he actually got a degree at Leeds. And that was that for a master's while he was here. He took a few classes, got his master's at Leeds. He came here with his master's, and so he's been here the past 6 years working on understanding tornado genesis. He's worked with the numerical model. He's gone to lots of conferences, and he's developed quite an expertise. So this is his Ph.D. defense, and I'll leave it at that. Let you talk.
All right, thanks, Greg. Switch the lights on. All right, so I'm going to be discussing some of the research that I've done throughout the number of years that I've been here. First of all, kind of coming at tornado science from a theoretical standpoint and reevaluating some of the tools that we use to study rotation in supercells and how it might be augmented to produce a tornado. The culmination of the research it uses some numerical simulations with both the UW-AOS model of Greg Tripoli and the CM1 model, which are non-hydrostatic research models in the mesoscale research side of things. So first of all, we'll have a quick look at the outline for this talk. There'll be a quick background to give key information on supercells that will be relevant throughout the discussion. Then there'll be a motivation for what the talk will be provided, and then we'll go through the method of the approach, and then the results, and finally the culmination is a conceptual model of supercell tornado genesis that involves a helical interaction of vorticity. So we'll start off with the background. Quick. So supercells are quasi-steady propagating unicellular modes of convection. They rotate as opposed to any other types of convection, which sets them apart from other types of cellular convection. So this rotating updraft is known as a mesocyclone, and rotation aloft dynamically, rather than through buoyancy, sucks air upwards via dynamic low pressure. So in the words of Greg Tripoli, supercells suck. Because of the mesocyclone, because of the rotation in the supercell and the wind shear inherent in their environment, the outflow region and the inflow region of the supercell are separated. And so the longevity of these storms is much more significant than other types of cellular convection. Supercells in general are fairly predictable with enough convective available potential energy or conditional instability in the environment and vertical wind shear. Supercells will form if there is a forcing mechanism. But the subsequent evolution of the supercells in those environments is much less easy to predict, and it has a big impact on whether the storm can produce a tornado. So a couple of key concepts here. Supercells that generate cyclonic rotation and move to the right of the mean wind develop through interaction with what we call streamwise vorticity, which on the diagram here at the top left is just simply the dot product between the horizontal velocity vector and the horizontal vorticity vector here in green. So when winds strengthen and veer and change direction with height, as can be seen by this American football in the bottom left-hand corner of this figure, when a buoyant updraft is imposed on that, rotation can develop about the vertical axis. And so this is what is required to generate mid-level rotation of a supercell. So on the far left-hand side of this figure set, we have two conceptual environments. One in which an updraft, which is the white bump in what is an isentropic surface, in green here, is in a crosswise, an environment characterized by crosswise vorticity, one in which the wind shear does not change both speed and direction significantly with height, leading to a predominant mode of crosswise vorticity in the storm relative environment. Once an updraft tilts this orientation of vorticity, the rotation does not develop about the vertical axis, rather it develops on the peripheries of the updraft. But in the streamwise vorticity case, the storm relative flow ascends in the direction that the vorticity vector is pointing, and such the rotation develops about the vertical axis. In the second panel here, we have the same cases for the top case and the evolution of a supercell in that environment through tilting crosswise vorticity. If we tilt crosswise vorticity in the region of the updraft, the vortex lines, which are everywhere parallel to the local vorticity vector, they are arched up over the top of the supercell and produce rotation on either side. As we discussed a minute ago, supercells suck air up dynamically, and this rotation that develops, because it's not superposed with the updraft, ends up generating an upward directed dynamic pressure gradient force that forces new updraft development on the flanks. This is known as the supercell splitting process and can be seen here on the top. Meanwhile, if we have an environment characterized by streamwise vorticity, the cyclonic split of the initial supercell updraft is favored. And this is because it's got positive streamwise vorticity in its inflow, and it tilts it and develops rotation, whereas the left mover is suppressed. So in environments with storm relative crosswise vorticity, the supercells will tend to undergo a lot of splitting process. And this is known as the nonlinear supercell propagation mechanism. In environments with significant streamwise vorticity in the storm relative environment, the distribution, and I won't go through this, but the distribution of pressure gradients across the updraft leads to continual forcing via the dynamic pressure gradient on the right side looking downwind of the initial updraft. And so therefore, a supercell, cyclonic supercell involving in an environment with a lot of streamwise vorticity will linearly propagate to the right. And so this is known as the linear supercell propagation mechanism. From here in, we'll talk about this subset of supercells, these cyclonic right movers, because of their prevalence across the United States and their dominance in producing the tornadoes that we're interested in. This is primarily because most of the environments that lead to supercell genesis, such as warm air advection and winds strengthening and veering with height, occur in developing mid-latitude cyclone warm sectors. And this is where the wind, as I just said, veers and strengthens with height. And so there's a prevalence of streamwise vorticity in the background environments for supercells across the United States. So while updrafts tilt and advect and stretch vorticity away from the surface to generate mid-level rotation, low-level rotation associated with tornado genesis occurs via the introduction of vorticity by downdrafts, where it is initially absent near the surface. So to look at an outflow or downdraft sort of conceptual diagram, there's a couple that I put up here that are used quite widely as kind of conceptual ideas of what the outflow structure in a supercell looks like. On the left, we have the classic Lemon and Doswell conceptual diagram, which shows, again, a cyclonic supercell with the updraft rotating upwards in a cyclonic manner in this region. And then the dominant downstream precipitation region is characterized by a downdraft, which is commonly referred to as the forward flank downdraft. And in the rear of the storm, where the hook echo is, we have another downdraft region known as the rear flank downdraft. In more recent kind of theory, it's been found that there's often kind of two quasi sort of convergence boundaries in the forward flank. and one more robust boundary in the rear flank. This boundary in the rear flank has sharp density gradients across it. However, the left flank boundary and the forward flank boundary have much less sharp gradients in density. And so rather than call them gust fronts, we tend to refer to them as convergence boundaries. So this is a supercell that I came too close to, and the supercell reflectivity on radar is here on the left, showing the forward flank downdraft regions with the heavy precipitation, and the RFD and hook echo region in the rear of the storm. And this notch here is known as the inflow notch, where the updraft is developing. And rotation develops typically on the left edge of the hook echo, looking downwind of the supercell propagation. And this is a nice little image out the back of my car as I drove through this region and looked back behind me. So I wouldn't advise doing things like that. So we've been through this. The difference between mid-level and low-level rotation is that downdrafts are necessary for low-level rotation. For tornadogenesis in supercells, air parcels that have acquired this type of rotation via interaction with the cold-pool regions in a supercell need to participate subsequently in the updraft for the rotation to be intensified by stretching to produce a tornado. So there's an additional requirement for a tornadogenesis over just simply developing low-level rotation, in that the parcels that have low-level rotation must be ingested up into the updraft. So how can rotation be generated in downdraft regions? There's a couple of primary kind of theoretical mechanisms by which this can occur. Over here on the right, we have the horizontal and vertical vorticity tendency equations. The first two terms here are associated with the tilting and stretching of vorticity, and then the third term on the right over here is associated with buoyancy gradients in the flow. And the last term is the frictional term. In the vertical vorticity equation, horizontal gradients of vertical motion will lead to tilting of initially horizontal vorticity up into the vertical axis. This term over here is particularly important and is known as the stretching term. We'll be talking about this quite a lot, and it is necessary, like we just said, for rotation to be intensified. So the two primary theoretical mechanisms are known as the barotropic and baroclinic mechanisms. The barotropic mechanism is associated with the tilting and stretching of vorticity. Barotropic vorticity is simply moved around in the flow and is not created, generated in the flow. However, the baroclinic effects associated with buoyancy gradients in the atmosphere generate vorticity. And so therefore, when we look at things like vortex lines, the vortex lines are not material surfaces in baroclinic atmospheres because they're continually being modified by the baroclinic effects that associated with buoyancy gradients. So how can we generate rotation in either of these cases? Well, consider a field of vortex lines on the left in this panel A here of Straka et al. 2007. If a downdraft is imposed on this, it can theoretically depress the vortex lines in the environment and lead to a counter-rotating couplet, as it's called, on either side of it, a cyclonic and an anticyclonic branch. Also, if a downdraft descends, it may interact. Let's say there's an updraft where this funny hand is. As it subsides near the updraft, the differential vertical motion across it will tend to lead to a tilting of the vorticity that's generated baroclinically on the edge of the downdraft. And this is the vortex line arching theory of Markowski here on the left, and we'll look at this in a little bit more detail here in a second. So the baroclinic mechanism has become the dominant way in which we think that vertical vorticity near the ground is generated. Such a mechanism can occur along a flow trajectory that descends through the periphery of a downdraft. The red vectors here are the barotropic vorticity vectors, and the blue are the baroclinic vorticity vectors. As the flow trajectory descends, the barotropic vorticity vector tilts with the flow. But through continued baroclinic production along the trajectory, the baroclinic vorticity vector becomes elevated with respect to the trajectory. And through what we refer to as the barotropic mechanism, or barotropic effect, sorry, which I've kind of put a couple of lines on here trying to denote the difference in magnitude of the flow at low levels versus aloft. So if you imagine this descending, it'll accelerate out like that. This is the kind of mechanism by which vorticity vectors associated with baroclinic vorticity can be tilted into the vertical during the descent through the periphery of a downdraft. This will become important later on when we discuss some of the theories behind vorticity production in the storms that we were looking at. So we talked about the fact that for tornadoes to form, there needs to be an interaction between the storm's rotating updraft aloft and the vorticity that was produced by either the baroclinic or the barotropic mechanisms in the cold pool regions. On the left here, we can see from Kofer and Parker, who ran similar simulations, the ones that we'll be presenting here today. They ran a bunch of trajectories through the cold pools into the region where the vertical vorticity was most intense. And they found that none of them really ascended much above 500 meters and no more than 1 kilometer above the ground during their life cycle. However, the tornadic trajectories, following a similar path, then ascended very deep within the storm, indicating that they'd undergone an interactive process with the updraft aloft. So some of the proposed mechanisms by which this interaction between the vorticity and the updraft can take place is through the dynamic lifting of air that we discussed at the start of the presentation. The reason that buoyancy is not directly important in this layer is that the level of free convection, or where parcels become unstable through buoyancy and accelerate in the vertical, is well above the level at which the baroclinic and barotropic mechanisms associated with downdraft evolution will generate vorticity. So there needs to be a role of dynamic rotational structures in order to lift the air from near the surface. So by looking at the divergence equation, or this is the diagnostic pressure equation that results from taking the three-dimensional divergence of the momentum equations, we are left with effects associated with dynamics, these terms here on the left, and buoyancy. In terms of the Coriolis effect, the scales at which we're interested in for rotation on the tornado scale, we can neglect the last two terms. So, contributing to the pressure perturbation, the perturbation pressure in the atmosphere, we have dynamic contributions and buoyancy contributions. But dynamic contributions can come from spin, vorticity, or they can come from deformational effects. Deformational effects are associated with perturbation high pressure, and vorticity is associated with perturbation low pressure. So therefore then, if we have a lot of rotation aloft, but decreasing with height, then the pressure perturbation generated by the rotation aloft will tend to lead to an upward directed, what we call vertical perturbation pressure gradient force. And this has been theorized recently as a way in which the vorticity associated with the downdraft regions may interact, or what's known as, in the theory, is splicing, where the vortex lines associated with vorticity in the outflow region are severed and reattached to that associated with the mesocyclone. So some of the theories for the development of the actual vortex associated with a tornado, originally there was this hypothesis that it occurred through a descent of the rotation steadily from aloft. This is because we saw what's known as a tornadic vortex signature, a TOR-S, aloft in radar prior to seeing a tornado on the ground. This has since been rather debunked because of the timescale that process would take, and it's just not observed. Vertical vorticity growth occurs extremely rapidly over the lowest few kilometers of the atmosphere during tornadogenesis. So Trapp and Davies-Jones proposed that if you have equal convergence over a deep layer of high angular momentum air, that rather than slowly bring in higher angular momentum and via its conservation lead to an increase in rotation, that it could occur over a large depth simultaneously, which is effectively the same as the low-level mesocyclone, which forms in the lowest 1 kilometer of the atmosphere, contracting to the scale of a tornado. So recent work by Leof in SSCC found the dominant role of a helical structure in their simulation of a violently tornadic supercell. This helical structure forms on the cool side of the forward flank, the forward flank downdraft boundary, and approaches the updraft from the north and ascends around the incipient tornadic vortex. On the right here, we can see pressure perturbation, and the darker greens associated with the lower pressure associated with the tornado. But off to the right of the tornado, which is to the north in this figure over here, there is substantial pressure perturbations associated with that helical structure. And so that's going to be important going on in this discussion. So taking a little bit of a turn, some of the relevant fluid dynamics research that I've been studying as a portion of my Ph.D. Is pertinent to bring up here in this discussion as well. So this image on the left here is what's known as flow separation, and it occurs in boundary layers, initially laminar in nature, that become unstable through a shock or some other type of disturbance. The significance of this is that the vortex lines associated with the flow can reconnect. So where they may be associated entirely with, or entirely horizontally oriented, once this shock occurs, they can actually become, through deformational effects, rooted to the ground. And so this type of structure looks very similar to some of the types of structures that we see in an atmospheric boundary layer associated with surging downdrafts or surging momentum in the boundary layer. This is another interesting comparison here. Behind jet engines, extreme turbulence can occur through a very similar shock-induced interaction of initially laminar flow and lead to what in the fluid dynamics literature is called span-wise rolls, which are these rolls you can see in the cloud here. We refer to them more frequently as crosswise oriented vortices as opposed to streamwise vortices. At the center of the head of the roll, this region of higher condensate here is actually associated with streamwise or helical vorticity. And this is because the flow is being accelerated in the direction of where the jet is moving, and there is actually a conversion between crosswise vorticity and streamwise vorticity in the direction of the acceleration. This on the right here is Fujita's downburst model, and it shows a baroclinic head developing in response to a microburst. And this baroclinic head here is very similar to the crosswise type roll structures that we see on the left behind the jet engine. So this is, excuse me. So this was provided by Alex Schuth, who's over in Lubbock, Texas. And he recently, using Ka-band vertically scanning mobile Doppler radar, looked through the outflow region of the supercell. This is the surface density, perturbation density potential temperature, where the blues are more dense regions relative to the environment, and the reds and the pinks are less dense regions.
Is that model data?
No, it's radar data.
It says model data. It's model data. How do you get theta roll prime from a radar?
No, at least in my communication with him, he said that.
Simulation.
Okay, well, either way, if it's simulation data, then either way, the talking with Alex, he has found these structures in the real atmosphere. And so here on the top right, we can actually see Streamwise vorticity magnitude plotted here, and at the head of this density surge, or the edge of the dense air, we have a maxima in Streamwise vorticity, similar to what we were discussing.
If you would detect Streamwise vorticity with a radar, you win a prize.
Okay. So I guess this is model data then from Alex Schuth, rather than observation. Sorry about that. So flow, we talked about flow separation in a boundary there, but what about the reconnection or interaction of the separated flows? So work by Wu et al. In the fluid dynamics research community has shown that separated flows with that develop vorticity can undergo a helical interaction after the separation. So what we're looking at here is flow past an obstacle. And as the flow past the obstacle develops vorticity through friction with the obstacle, the one on the trajectories here on the top have developed rotation in response to that addition of vorticity. Subsequently, the separated flow then undergoes an interaction through vortex dynamics. On the right here is a simulation of what we were looking at in a physical flow behind a jet engine. And what we can see here in green is the crosswise component of the vorticity, and the red is the streamwise component of the vorticity. So this is demonstrating the conversion of crosswise vorticity into streamwise vorticity at the head of this rod. So some of the relevant, other relevant fluid dynamics research that I'll be discussing further once I've shown some of the results is a helical interaction of vortices can take place when two streamwise vortices are parallel. This is known as a winding process, and they do not actually reconnect with one another, they simply wind around one another in this model. However, if they become oriented perpendicular to one another, then the vortex lines, which cannot terminate in the interior of the fluid, actually can sever and reconnect. And so this is going to be important when we talk about the model later on and how this process may be occurring in the atmosphere. So motivation for the recent Ph.D. work, broadly speaking, during the last sort of 30 to 40 years, our lead time for tornado genesis in supercells and our probability of detecting them has improved fairly steadily with the introduction of the WSR-88D network and its subsequent improvement. However, our false alarm ratio, which is the ratio of the number of times we successfully, our tornado warnings are successful, has remained fairly steady at about 75% failure rate. And seeing as only 25% of supercells actually produce tornadoes, the rate is not great. More specifically, for my PhD research, the vorticity tendency analysis, so the equations that I introduced earlier, the horizontal and vertical vorticity tendency equations, are the predominant means by which to study the evolution of rotation in supercells at the moment. So the dynamic mechanisms of vortex development, rotation development, cannot be afforded directly through the vorticity approach, because vorticity is associated with shear and rotation, which we will talk about in a little more detail in a second. And so by this mechanism alone, it is not possible to tell the dynamical mechanisms behind the development of rotation. So another motivation is that significant horizontal and vertical vorticity is present in all supercells, or at least all surface-based supercells have significant vertical vorticity at the surface. But very few produce tornadoes. So that's why do most of them have a lot of vorticity, but not go on to actually generate the rotation associated with a tornado? There's so much information in the total vorticity field that it's often difficult to identify what may be important within that information. So, as we just looked at the recent work by Dr. Rohr, I isolated a dominant helical structure that appeared to play a role in tornadogenesis in their simulation. The vorticity framework alone doesn't measure the intensity of helical versus crosswise structures. So with the knowledge that helical structures are important in supercell tornadogenesis, it's critical that we develop adequate diagnostic approach to study the differences between helical structures and crosswise oriented structures. So it's generally accepted, as I said earlier, that the baroclinic vorticity production mechanism is the dominant mechanism by which low-level vorticity is generated under supercells. But that rotation needs to be ingested into the updraft, like we said. The dynamic lifting mechanism broadly explains the observed correlations between environments with high streamwise vorticity and their storm relative inflows and the likelihood that they'll produce a tornado. But explicitly from a dynamical standpoint, it doesn't offer an adequate method of understanding. There's also been the theory of vortex line splicing as a vertical connection mechanism, and yet it's still unclear of how this process may occur. So moving on to the method of my approach, I began by looking into the fluid dynamics literature. The fluid dynamics literature is full of information about structures, rotational structures in turbulence. And so the problems that they've encountered identifying or separating rotation or vortex structures from the full flow field has meant that there's a lot of different methodology out there for interpreting what is a rotational structure versus what is just plain shear. So I use that to distinguish three-dimensional rotation from the total vorticity field in numerical simulations that we did here in Madison. I then took that theory and extended it to measure the magnitude of the helical component of the rotation once I found the three-dimensional component of the rotation. Thereafterwards, the approach was to apply the new diagnostic methods to see if we could isolate some structures that may be critical in the tornadogenesis process that may play a role in that communication between the low-level vorticity and the rotating updraft. So the numerical simulations presented here were run with two non-hydrostatic mesoscale models. one again is the UW-AOS, and the other is the CM1. The information is up here. I'm not going to go into specifics other than that the horizontal grid resolution for both was 120 meters, and the vertical grid resolution was 40 meters over the lowest 1.5 kilometers, and then stretched in the vertical to approximately 360 meters. There are differences between the two models, and although it's kind of outside of the scope of this study to really address that, we're kind of using the two models to kind of test the veracity of some of the theory that we're developing in using the diagnostic approach. So how did we simulate supercells in using these numerical models? Well, we used recent data collected in the Vortex 2 campaign by compositing a series of tornadic soundings and radio sondes that were launched in the inflow regions, uncontaminated inflow regions of supercells that produced tornadoes and supercells that didn't. And so the resulting composite sounding used to initialize the tornadic portion of the simulations herein, it has these thermodynamic and kinematic characteristics. There's clearly a lot of cape needed for the energy for the updraft in this environment, and the wind, as can be seen on the photograph here, veers and strengthens with height considerably. So this is clearly quite a favorable environment for supercells and potentially for tornadoes. Meanwhile, at first glance, the non-tornadic sounding doesn't seem particularly different. We still have a rather significant amount of convective available potential energy, and the wind also veers and strengthens with height. A little closer inspection, though, will isolate something that is quite critical to the development of tornadoes in supercells. And that is this kink here in the lower portion of the photograph. If I superpose the two, you can see the difference. The purple here is the non-tornadic environment, and the red is the tornadic environment. You can see that there is a sharp kink in the wind profile, or the photograph, at this height, which is approximately 500 meters above the surface. So within the lowest 500 meters above the surface then, in the non-tornadic environment, if we look at a bunkers-derived storm motion, which is that way, and we look at the storm relative wind, which is taking V minus the storm motion, we see that the vorticity vectors, which point perpendicular to the photograph, are predominantly streamwise over the lowest 500 meters or kilometer in the tornadic environment, and yet they are more predominantly crosswise in orientation in the non-tornadic environment. This is important because, like we said, streamwise vorticity can be tilted and stretched and intensified, whereas crosswise vorticity leads to counter-rotating vortices that are not superposed with the vertical motion. Finally, we employ the use of an idealized sounding that has been run for many, many years to confirm kind of some of the results attained in using the new Vortex 2 composite soundings. To kind of look at some of the processes going on in the Vortex 2 simulations and see if they're going on in other types of environment too.
Are you sure that's the idealized Weisman-Klemp sounding?
It's slightly modified by Greg Tripoli. Yeah. So it's been edited a little bit on the upper troposphere.
Or smoothed it a little bit,
Yeah.
get rid of some of the kinks.
Yeah. So we're going to be discussing some dominant regions around a supercell in the results of this research. And so I just want to point them out on kind of a characteristic surface density field, perturbation density field here in the color shading on the surface. So this region at the rear, as we discussed earlier, associated with the hook echo region of the supercell, is known as the rear flank region. This wedge, extending to the northeast of the updraft and then back to the northwest, where the majority of these supercells dense areas in this storm, is going to be referred to as the left flank of the supercell. And this region out in front is going to be referred to as the forward flank inflow region. And that's an important distinction because whilst the forward flank is, has considerable precipitation, in supercells, especially the ones we ran with the tornadic environment, the inflow trajectories tend to come from the east-northeast. And so whilst it is characterized by precipitation, it is also characterized by inflowing air into the supercell. And then this region broadly to the southeast of the storm will be called the inflow region. And the locations marked by these stars here are the characteristic place that I chose to take vertical profiles or soundings using the model-derived data for analysis. So going back to the concept of vorticity versus rotation, here on the left we have a theoretical set of fluid parcels that are subject to pure shearing motion. The pure shearing motion will lead to a deformation of the parcels and a rotation of the parcels. Rigid body rotation will just lead to a rotation of the fluid parcels. And a pure, what is referred to in fluid dynamics as irrotational straining field, will just lead to a deformation of the fluid parcels. This is a figure from a paper submitted a year or two ago, and the top here is, the top part is a line associated with shear, and in this line of shear, the divergence tendency or the effect on the pressure field is 0 because vorticity is equal in magnitude in shear lines to deformation. And so the net effect on the pressure field is 0. In a region of pure rotation, like here over on the left, and these are not vectors by the way, it was pointed out to me when I submitted the paper, the net effect of rotation is to generate a local pressure minimum by producing an outward directed pull on via inertia. Therefore, we can separate the inertial field, the advection field, into effects associated with vorticity and deformation. And so this parameter over here, which we refer to as the square of the inertial frequency, is effectively the square of the vorticity magnitude minus the square of three-dimensional deformation. On the right here, we have something that I've referred to as rotational vorticity, following from Kohler in 2007, who defined something similar. And effectively what we do here with the rotational vorticity is we simply subtract out the shear component of the vorticity, which leaves the rotation the vorticity associated with the rotation. So, as we discussed, helical vortices have mass flux through them, through their vortex cores, but crosswise vortices don't. And so, as a result of this difference, the pressure forcing associated with accelerations at the upper end of a helical vortex can be communicated down to the lower portions of the vortex, through the mass flux through the vortex. Whereas this process does not occur, or at least very efficiently, in a crosswise sense, because there is no mass flux or no flow penetration into the vortex.
What about a two-cell vortex?
Sorry?
A two-cell vortex.
Two-cell vortex.
There's a downdraft in the center.
Right, so they're both helical.
There's no crosswise anything in there?
There's crosswise around it, but there's two helical vortices. Because I've actually got an interesting figure that I can show later on But the flow in the core is helical, and the flow at the end wall region is helical. So it's two helical vortices. So the interaction and the transition between the two orientations of vortices is important in supercells, and we'll look at this in a second. So therefore, using the rotational vorticity parameter as a basis, I simply took the dot product of that vorticity field with the velocity field, just in the same way as we calculate streamwise vorticity. But now, rather than getting the whole wealth of the information of the vorticity field, we now just have the rotational component of the vorticity field, and so we can define helical vortices, helical rotation, as opposed to just helicity. And the difference being that in the helical rotation, the flow is moving in a rotating sense about the axis, as opposed to just being associated with shear.
Is that different than streamwise or the same?
So it's an interesting distinction, because streamwise vorticity can be associated with shear or rotation. So helical vortices have a lot of streamwise vortex lines associated with them, but streamwise vortex lines can exist in a layer of shear as well. So examples of using the diagnostics, on the right here we have an image of total vorticity magnitude as a volume rendering in a supercell, and then I squared and the del squared P, or the pressure field. And so it's apparent that the I squared diagnostic removes a lot of the noise from the vorticity field by isolating the three-dimensional structures. Additionally, the I squared parameter is Galilean invariant. And this is important because the total vorticity field is Galilean invariant. And so if you're trying to measure the rotational component of the vorticity field, you'd like your diagnostic of such to also be Galilean invariant. So imposing a mean wind on a vortex, which would lead to an open flow pattern like this, would still lead to the same structure of the I squared field. So examples of applying these diagnostics, this is the May 24 simulation of Dr. Ross. The total vorticity field is up here on the left, and then the rotational vorticity field at the same magnitude is here on the right. And on the bottom left, we have the rotational helicity field, which is now gray, and the vertical vorticity field. The interesting thing is that while these vortices here are associated with vertical component of vorticity, the red isosurface here, they're not associated until their upper portions with rotational helicity. So this shows that you can distinguish between types of vortices by using the rotational helicity parameter with other types of diagnostic that we already use. And this is an example of such a helical structure that can be depicted with the rotational helicity field. So onto the simulations and the results. Tornado-like vortex. What does tornado-like vortex mean? Well, in numerical simulations where we don't adequately resolve the tornado vortex, we can't really attain the types of magnitude that we physically see in the real atmosphere. And so rather than call them tornadoes, we'll be referring to them here as TLVs, tornado-like vortices.
I got a question.
Yeah.
If it's small enough vortex and it has strong intensity, but there's no condensation funnel, wouldn't that also be a tornado-like vortex? Because the meteorological definition of a tornado is a condensation funnel.
Well, no, it's a violently rotating column of air.
It doesn't have to be condensation.
Yeah, it doesn't have to. So,
It doesn't have to have a condensation?
No.
I thought it does.
No.
Okay.
because I mean, you frequently see tornadoes without condensation funnels extended to the surface. So we ran a bunch of different simulations, specifically using the tornadic vortex 2 environment. We ran 10-member ensemble, and then picked a characteristic run, which we're going to refer to here as TOR-S, using the NMS model. And for each of the runs in the tornadic environment, they all produced what we call TLVs. However, they occurred at very different times throughout the simulation. So what we're looking at here is model-derived integral data from the NMS for the TOR-S simulation. On the left over here, in the red, we have minimum pressure perturbation. And in blue, we have rotational helicity, like we just discussed. So we can see here, where the pressure begins to fall, that we have likely the development of a TLV. The pressure for the remainder of the simulation remains about -1 to -2 hectopascals, and it falls closer to -10 pretty rapidly. And so when we plot that against surface vertical vorticity, we can also see a rapid increase. These values are way off. They're an order of magnitude off, so like that. But the surface vertical vorticity increasing alongside the minimum surface pressure is indicative of a TLV. However, we're going to need to do more analysis to work out whether it is really a TLV and...
Wait. What's that big blue hump at 4,500 on the left that's not matched by any pressure change?
Yep, so this is rotational helicity.
Right.
And so...
You have a bunch of rotational helicity, but you have no pressure signal?
So this is, bear in mind, this is across the whole domain. And so we are just simply looking at regions of rotational helicity is the dot product between the velocity vector and the rotational vorticity
I'm just
vector.
trying to understand this figure. What does it tell me?
Right, well, so it's showing you where the tornado is forming, and so that we can look relative to that at things that we may be interested in the simulation. The reason I'm showing you this is that prior to tornadogenesis, in all of the simulations that I analyzed, there was a maxima in the rotational helicity field prior to the development of the tornado. Now, in the vertical vorticity field, they almost one-for-one match each other, which we'd expect, because the correlation between substantial pressure minima and vertical vorticity makes sense. But in the rotational helicity field, which again is the dot product of the velocity and the rotational vorticity, so intense accelerations along the rotational vorticity vector will lead to maxima and rotational helicity where there may not be substantial pressure drop. And because the rotational helicity field doesn't vary as much as the vorticity field, we're able to isolate events like this from the full data
You
set.
can have a really rapidly, basically rotating vortex that's beautifully exhibiting helicity that has no pressure drop. It just seems weird to me. I just don't understand. I would
No.
expect to see it somewhat matching.
So they do well, but so that goes back down to the question of whether the TLV or the tornado vortex is helical or crosswise. So they may match, and in this region right here, they do quite well tie together because the TLV, as will be shown later on, actually has a helical component to it. But this part right here is associated, as will be shown, with more kind of accelerating helical structures in the horizontal and not vertically oriented vortices. So this is the surface condensate field calculated in the NMS, and we'll just watch the evolution of it. What you're looking at here is the rear flank and hook echo, and then the forward flank regions. And we can see a lot of condensate reaching the surface in this region around where the TLV begins to develop, around 55 to 5,800 seconds. This is the density field that's associated with that surface condensate. And at first it looks fairly diffuse and not particularly robust. But around about the 4,800 time, we get a surge in the density at this level, and this creates a much sharper, more distinctive boundary in the supercell. Interestingly, lower density air gets mixed in from the environment into the outflow and around the developing TLV during this time. So for the subsequent analysis, we focus a little bit more specifically, rather than the integral data, which was over the entire domain. We're looking at different regions of the storm. The red dot here is the maximum updraft center, such that when we take a box area, the box remains quasi-steady relative to the storm motion. This is the box we'll be using for what we call the storm domain, and then this will be the box that we use for the outflow domain. The reason that we do this is that once you include the tornado in the box, it obviously dominates the signal in a lot of fields, and so it can be difficult to pull out some of the information. However, as will be shown, rotational helicity does not suffer from this aspect. So this is rotational helicity. We are looking at the genesis phase of the TOR-S simulation. In the top panel, we have the full storm domain. And in the bottom panel, we have just the outflow domain. What is interesting and immediately apparent when looking at this data is that there is an obvious interaction or upward development of rotational helicity around about 52 to 5400 seconds, which is right in the time of genesis of the TLV in the simulation. As we can see in the storm domain, while the storm domain has helical flow in this layer near the surface, which is 0 to 2 kilometers, this is absent in the outflow domain. This is indicative of us capturing the helical flow associated with the TLV. And what we can see, the reason I'm pointing this out is that when we go to things like vorticity, there are substantial differences between looking at the storm domain and looking at just the outflow region domain. In looking at just the outflow region, the vorticity very nicely picks up on an upward propagating pressure minima, which is here over on the left. But if we look over into the storm domain, there's so much going on in the rear flank of the supercell that we just completely lose the signal of the upward propagation in the vorticity.
Did you get that signal by changing the color map? What colors?
No, I've played around with it for a long time. No, you can't. So this is a close-up of that interaction. On the left, we have time versus height plot of the vertical vorticity field. And on the right, we have time versus height plot of the rotational helicity field. At the time, a relative maximum in the rotational helicity, which seems to be associated with the 1,000 to 1,500 level, and then a separate rotational helicity maxima at approximately 500 meters above the ground, appear to undergo an interaction, or what I'm referring to herein as a coupling process. Right at this point in time, vertical vorticity explodes from the surface upwards. And so we are going to be focusing on what is going on during this time. So the panels on the left are the surface perturbation density, and the panels on the right are the same times, but looking at isosurface, the gray isosurface, of rotational helicity. And so at first, like we saw in the loop, the density is fairly diffuse at the first time, and we don't really get much of a signal at low levels in the rotational helicity field. We do, however, have a helical structure arriving from the forward flank, which is associated with the updraft's inflow. As we get this kind of momentum surge in the supercell, along its periphery, we actually start to develop helical rotation. And this, as the boundary intensifies along with it. And interestingly, whilst this occurs, the helical flow associated with the inflow, which is elevated above this, actually intensifies as well, and the two actually merge into one helical structure, arriving from the north of the updraft.
So is that surge a push or is it being pulled?
It's definitely being pushed in the NMS because you get, and I'll show this in the next figure. So, this is condensate, and you get a really big surge of condensate in the forward flank region.
So do you get a crosswise like roll vortex like you would? But that's crosswise, not helical, right?
No, right, exactly. So, yep, I'm getting that. So, as this causes a crosswise type roll that accelerates out along the surface, recalling the theory that I was discussing earlier about accelerating in the direction of motion, due to the baroclinic effect of the rotating head, which is crosswise, and the acceleration downstream, you end up with a conversion from crosswise to streamwise vorticity in the head region. And so you can see here divergence, the convergence is plotted at the surface and surface wind bars. Underneath this surge, you get a large region of divergence along the periphery. We're now looking to the south from the north through the outflow. And so along the periphery is where Dr. Rolf and I were discussing, is the vorticity crosswise in orientation, or is it streamwise? Through the rotational helicity field, we can see that a portion of it, at least, becomes helical. So, interestingly, if we plot, and this may help visualize this a bit better, if we plot a cross-section through this structure and through that density gradient, a vertical cross-section of perturbation equivalent potential temperature, what we see, and this is the baroclinic crosswise head of that surge that we were discussing, and in the head region, like was shown on the model-derived radar data, we actually begin to develop helical rotation along the axis in the direction of the acceleration. And so, in response to this, interestingly, we have a downward ingestion of less dense air from the ambient environment into the outflow. So to kind of confirm this downward directed acceleration of the ambient air, we also look at the potential temperature field in a vertical cross-section. We were looking from the north in the direction of the surge. We're now looking at the surge coming out of the page at us. And in this region right here is where the rotational helicity maxima is organizing at low levels. And it appears to be associated with, on the cold side of the boundary, with higher theta values, which indicates, or higher potential temperature values, which indicates a dynamic acceleration of the ambient air into.
Where's the updraft?
The updraft is right here.
Luke, how much longer you got? It's been about an hour already.
Okay. All 5 minutes. So when the structure propagates toward the updraft, it actually becomes sort of elevated and tilted into the updraft and is ingested at the base of the north of the updraft. This isosurface here, the green isosurface, is 20 meters per second vertical motion. And the gray isosurface is, as before, is the rotational helicity. The yellow isosurface is pressure perturbation at 2 hectopascals. And what we can see in response to this structure is a lowering of the pressure to the north of the updraft where this structure is being tilted upwards. The red isosurface here is vertical vorticity. And because of its helical nature, vertical vorticity develops along the periphery and then is ingested into the updraft. This is the structure from the other side, and you can see the pressure perturbation associated with it, and then the TLV in terms of the pressure field developing at the rear. I'll skip this one. So this one's interesting. This is what we were discussing earlier with the two-cell vortex. This is rotational helicity colored by W, by vertical motion. And you can see at the core of the TLV, at its strongest period, you have a rotational helicity maxima, which is actually associated with downward motion at the core of the tornado. So it's really interesting to see this. It really only picks up on this structure, and it's very nice to see. There are other interesting helical interactions going on that we can afford with the use of the rotational helicity parameter, and during one of which, this is a re-intensification period of the TLV in the tornado simulation. Again, W in green, rotational helicity in gray. We can see the two helical structures superpose with time, and you get explosive growth of the TLV. I'm going to skip through this pretty quickly. This is the CM1 simulation. This is a time height plot of rotational helicity. On the top, this is 4 kilometers, and this is a 600-second period during the genesis phase of the TLV in the CM1 simulation. And this is vertical vorticity here that grows upwards from the surface with time, and it is correlated in time height space with the upper propagation of the rotational helicity maxima. What we see in the isosurface data is a maxima, again, along a similar convergence boundary to the north of the updraft in rotational helicity, the gray isosurface here. Again, the red isosurface is vertical vorticity, and we can see vertical vorticity transport along that helical structure. This is the total streamwise vorticity, not just the helical component now, and so you could see a lot more information in here, but along this boundary, what's interesting is you get a rolling of the streamwise vorticity over that structure. So I'm going to skip over failure in the interest of time, but I wanted to show some trajectories from the Weisman-Klemp idealized sounding. So now this is a completely different sounding that we are using to study a very similar process. We're looking at the same convergence boundary to the north of the updraft in an idealized supercell using the Weisman-Klemp sounding. Again, the isosurface that's red is vertical vorticity, but now the purple is the rotational helicity. And the trajectories that are initiated in the structure and those in behind undergo a helical winding process. I'll play that back one more time. During the tornado development. So these are some characteristic parcels that entered the TLV. Baroclinic vorticity production was determined to be the most substantial production mechanism of the vorticity component. What is very interesting here is this sudden dip in the vertical vorticity magnitude between 300 and 400 seconds. And this is right in the period when they interact with the helical structure. What is happening here is that they're being violently tilted downwards on one side of the helical structure and then violently tilted upwards and subsequently stretched on the warm side of the helical structure. This is an image of inflow parcels going over the top of the helical structure and then winding around the parcels associated with the downdraft. This is an image of them being forced from the environment into the outflow region of the supercell here. Notice how the surface will get warmer when this is theta E. So relatively high theta E develops in this region in response to them being ingested, because they are being dynamically forced into the outflow before they ascend to the highest model level. So as a result of this numerical investigation of tornadogenesis with the rotational helicity and rotational vorticity diagnostics, we can define a paradigm based on a helical interactive process. This figure really jumped out at me when I was doing research in preparation. This is it's very difficult to see, and fluid dynamicists are not very good with making pretty pictures like we are, and nor am I apparently, but what we have here is a separated boundary layer flow. With this white sheet here is a vortex sheet, which is rolling up very similar to how we saw the crosswise rolls earlier on in this talk. At the center, we have vortex lines. Interestingly, when flow undergoes a separation and reconnection process, the vortex lines may terminate at the ground and extend off into the plane. This is the vertical plane. So this image here is very similar to the leading edge of a helical structure on a downdraft surge. The helical flow at the center of the structure here is associated with vertical vorticity on its warm edge, and the streamwise vorticity lines may actually end up going up into the updraft. So I'm not very good with Adobe Illustrator, but this is a very rough conceptual idea of what I think is going on here. The inflow parcel from the forward flank region that approaches that convergence boundary is in the red here, and this structure here is the roll structure that we've been talking about on the edge of the convergence boundary. The blue is an outflow parcel that's descending and generating baroclinic vorticity. As a result of this intensification of the surge, there's strong divergence in this region on the cool side of this structure. That leads to a dynamic acceleration of the inflow parcel that is characterized by significant streamwise vorticity. Similarly to this process, on the left, the vortex lines can intertwine. If you twine two lines together and pull, then you have what I'm referring to here as a coupled helical structure. It's coupled because the vorticity is from two separate origins, from the outflow and baroclinically generated, and from the inflow and associated with the environment. The significance of this is the dashed line here that's blue and red indicates the structure that is now coupled, is that the red inflow vortex line is associated with positively buoyant air because it has been drawn dynamically and down to the surface where it doesn't really want to be. So like pulling a spring and letting it go, it'll shoot back up in, this is the vertical plane here, into the updraft once the sign of the dynamic forcing reverses sign underneath, for example, the dynamic lifting of the low-level mesocyclone. Meanwhile, this can lead to the flow reconnective process, and the vortex line may, associated with the baroclinic vorticity of the outflow, can become part of the vorticity associated with the storm's inflow. Meanwhile, on the warm edge, so the outside edge of this structure, continued baroclinic vorticity production can lead to surface-based vertical vorticity growth that is effectively coupled dynamically, helically, to the updraft aloft, because the vortex lines associated with the outflow are now wound around or reattached to those associated with the updraft. So it is very, it's consistent with a lot of theory in that we need a lot of streamwise vorticity in the inflow, in that we need not too dense outflows for tornadoes because otherwise the the inflow could not penetrate into the cold pool and allow this coupling process to occur. And it also, via trajectory analysis, we showed that it was baroclinic vorticity production that dominated the vertical vorticity component of the structure. So it's consistent with a lot of current theories. To conclude, during this research, we kind of looked at some new approaches to studying rotation in supercells, particularly on the substorm scale, the sub-mesocyclonic scale. And we looked at helical versus crosswise vortices, and then applied that diagnostic to study supercell simulations in which we can resolve these structures adequately using Vortex to field campaign data with both the NMS and the CM1 research models. We were able to identify a dominant structure, very similar to the SVC in Orf-et-al, of helical flow that is seen to be associated with internal convergence boundaries. The interaction, the interactive effect of that structure with the low-level environmental flow appeared to lead to a coupling process and explosive upward growth of vertical vorticity from the surface, because we are effectively sealing the updraft with the ground during this process, which is why vertical vorticity can explode so rapidly upwards as we've seen in the time height analysis. This coupling mechanism was absent critically in the TLV failure and no TLV cases. So I won't go over that again. We'll talk about some future work. To understand this process, we need to do more rigorous analysis quantitatively. We need to apply vorticity tendencies and vertical motion tendencies along trajectory analysis, air passing trajectories, to determine quantitatively the reasons for the intensification of the helical structure, which is evident in all tornadic simulations that we did. We also want to test the environmental sensitivity of this process, of this helical process. We want to look at different thermodynamic and kinematic environmental structures and determine whether there is a signal that we can determine in the mesoscale environment that will be able to alert us of this effect. To study it, we would like to isolate the process in idealized downdraft experiments. And lastly, we want, ideally, we would develop a prognostic equation for rotation in order to do quantitative analysis on it. Okay, so some brief acknowledgements. I would just want to thank Greg Tripoli, my advisor, for at times driving me insane, but pushing me the extra yard for all these years and continuing to believe in me. And my committee members, Professors Jonathan Martin, Michael Morgan, Marcus Bucher, and Dr. Leorf, for offering support, advice, and encouragement. And Kelton Halbert in particular, who was incredibly helpful in getting me acquainted with the CM1 and with various technical issues that I ran into over the process of the last few months. So thank you for that. And Pete Pogrant, oh, I didn't fill in that one. Pete Pogrant for also, but he's not here, so it doesn't matter. Sorry, Pete. But Pete Pogrant also for just years of technical help.
Fill in the blank.
Sorry?
Years of fill in the blank.
Yeah. And so I always appreciate the help from Pete. And my girlfriend Kathy for putting up with me during this process, and at times I'm sure I could be quite difficult to deal with. Recently, my family and friends have been extremely supportive in the time that I needed it most, so I appreciate that. And to the rest of the AOS department for a lot of stimulating conversations over the years. So thank you very much.
All right, I think we'll take a few questions from, other than the committee, and then the committee will. Any questions?
How is the rotational parameter you've derived different than like the shear versus curvature parameter from like Johannes Dahl or Robert Davies Jones, or the streamwise versus crosswise from like Shankman and Roberts? Like where does it fit in those comparative frameworks of looking at rotational versus curvature, or streamwise versus crosswise?
So shear versus curvature vorticity is Galilean invariant in the way it's defined in the Dahl et al., or sorry, the Dahl framework. By defining it on a height surface or a pressure surface, flow does not move along height or pressure surfaces. And so by splitting the vorticity up into components of shear and rotation on a surface like that, it does not fully, because it's not Galilean invariant, it does not define the total quantity of shear or total quantity of curvature in the flow. And so some of the, interestingly, his findings of that being this conversion of curvature into shear, I suspect may be somewhat diluted by the fact that the shear component and the curvature component may not be the true rotation and shear in the flow.
So what about the streamwise versus crosswise budgets that you can do, where you can look at just the helical flow from a streamwise vorticity budget and isolate it that way?
Right. So in those budgets, the streamwise or the crosswise vorticity could be just associated with shear as well, or horizontal flow accelerations along a shear layer, for example. Whereas what we've done is removed the shear component and taken the dot product with the velocity field. Therefore, it actually measures helical rotation as opposed to just helicity, which is associated with shear and rotation, right? Does that make sense?
Any other questions? Okay, thank you all for coming. Want to take a break or just go straight?
No, we should probably just go straight.